Okay, so let's start. Okay, so the next speaker is Professor Berndtsson from Chalmers University of Technology. And he is the winner of the Frontiers of Science Award. And his title is Complex Brunn-Minkowski Theory and Some Uniqueness Theorems in Kähler Geometry. Let's welcome.
Thank you very much. And thanks very much for the invitation and the prize, of course. I should say that not only am I one of the older winners of the award, but it's also one of the oldest papers that is being awarded. So sometimes I might sound a little bit like a broken record when I talk about it. This is some old stuff, but that's the subject of the talk. So if you have never heard of it before, it's very good because then this lecture is for you. Okay, so let me see if I can do this. Yes, so first, so the subject is about convex geometry to some uniqueness problems in Kähler geometry. But the paper that I'm going to talk about is actually a part of a sort of bigger project. And I will start by describing the general framework, the general setup. This is supposed to be illustrated by the two figures there. And if you think they look the same or similar, that's supposed to be part of the point of the lecture. But let me explain more carefully what this is. On this side here, we have a complex fibration. So this set here, this domain, well, this manifold there is a complex manifold. And I will assume that it's a Kähler manifold. And this thing here is also a complex manifold. And I have a surjective holomorphic map that I call P here. Surjective means here also it's a subdifference, so that the differential is also surjective. And that means in particular that the fibers here, so this is one typical fiber, so this is Y here, and here is XY. All those fibers, they are manifolds because it's a proper map, and they're also non-singular because it's a submersion. Oops. Okay, and now in addition to this, I will assume the existence of a line bundle over the total space, so that is called L. That's a holomorphic Hermitian line bundle over there. And it's equipped with a metric that I usually write in the form e to the minus phi there. So this is actually only locally defined, but I use that as a symbol for the metric e to the minus phi. And I will assume that it's semi-positively curved, meaning that I d bar of phi is always greater than or equal to 0. Okay, so that's the setup on this side. Now, for each such fiber, we can look at a certain vector space of holomorphic objects. So these are holomorphic sections over the fiber of a certain line bundle, which is just the global line bundle L restricted to the fiber. That's the last part there. And then it's the canonical bundle of the fiber, called K of Xi. So those are, that's the bundle of holomorphic forms of maximal degree on the fiber. And so you can think of this EY here as a space of holomorphic N0 forms with values in L. And this here, EY, is a finite dimensional vector space. And we can equip it with a norm, an L2 norm, and that's just defined here. You say that the L2 norm of U is like it's the integral over the fiber of U wedge U bar. So since U is a form, U wedge U bar will be a volume element. And since it takes values in L, this becomes some sort of bundle valued thing. But when I multiply it by the metric, then it becomes globally defined. So I can integrate it. I could have looked also at just the space of holomorphic sections of L. And then I would like to take the L2 norms of the holomorphic sections U over there. But then I would need, in addition to introduce some measure with respect to which I integrate. And I don't want to do that because then the whole theory would depend on the choice of that metric and that measure, and that could be difficult. So instead, I look at n forms with values in the line bundle, and I get this L2 norm there. Now, as y varies, I get a family of vector spaces that are parametrized by this. And the conclusion of the theorem is that, so I assume, as I said, that the total space is Kähler. Then if I take the disjoint union of all these vector spaces, I get a vector bundle, not just a family of vector spaces, but I get a locally trivial holomorphic vector bundle. And this also is equipped with a norm, namely this norm there. So I can, on this vector bundle, there is defined the Chern connection. And the conclusion of the theorem is that this holomorphic Hermitian vector bundle has semi-positive curvature. And for specialists, it's semi-positively curved in the sense of Nakano, which is the strongest notion of curvature, but that will play no role in my lecture today. So this
active dimension is
the dimension will be constant. Yeah. What?
Dimension is constant.
Yes, yes, it will be. Yeah, that's a consequence of the assumptions. Yeah. Yeah. Yes. Yeah. So, in case when the line bundle L is trivial, this is fairly standard, but it actually follows in this setting also as well by an application essentially of the Osada-Takegoshi extension theorem. Okay, so that's the basic theorem. But now I'm going to specialize it eventually to more special situations. So let me first say that the special case of this theorem is classical. It is due to Griffiths and Fujita, and it's a consequence of Griffiths' theory of variation of Hodge structures. And that's the case when the bundle L here, when the bundle L there is trivial, then I just have scalar valued holomorphic n forms. And then it follows by Griffiths' theory that this bundle will be positively curved in that sense, in that way. So that was, I think, stressed and developed by Fujita. But, well, it's not very important for the talk, but if you look at Griffiths' proof of the theorem, it's actually quite different from the proof, from my proof of this more general version, which I'm actually not going to give. But Griffiths' proof was based on regarding this bundle here as a sub-bundle of another holomorphic vector bundle, actually a flat vector bundle, which is called the Hodge bundle in algebraic geometry. And it's not so easy to generalize to the twisted case when you twist with a line bundle. Okay, now I would like to, since the name Brunn-Minkowski appeared in the title, I would like to give a comparison to Brunn-Minkowski theory. And that's the other picture there, which then looks pretty similar. I'm always pressing, now I'm really in trouble here. What can I, let me see here. 3 7-day trial. Okay, so then I'm far away. Yeah, so let me compare it very roughly with Brunn-Minkowski theory. Then you are in Rn instead, and you single out one of the variables here, x1. And then you have Rn minus 1 up there, and you have a convex body instead of a complex manifold. And then you, instead of the holomorphic map, you just have the projection down to the x1 axis. And you still have the slices, and they will then be n minus 1 dimensional convex bodies, and they will move. And the Brunn-Minkowski theory says that if you look at the volume, so if I call them also, I call this convex body x here, I call those x, well, call this y, xy. Then Brunn-Minkowski says that the logarithm of the volume of xy, well, the function the function that maps y to this is concave. That's the one statement of the Brunn-Minkowski theorem. And I hope that you see the analogy between the two. So the replacement for concavity is positive curvature, and the replacement for the holomorphic map is just a linear projection. Okay, it will come in a little while, because in this will actually correspond more to Griffith's theorem, and there is no line bundle there. So in that case, we can state the theorem. Well, let me do it right away, actually. So here we just have the volume of this. Moreover, there is a more general, if you have a convex function, phi convex, defined on the total space, then you can look at y maps to logarithm of the integral over xy e to the phi I. So I restrict phi here, and you integrate with respect to the Lebesgue measure. Then this is also concave. So that would correspond to the twisted case then when you have a line bundle. And as I will recall in a little while, this generalization of Brunn-Minkowski is called Prekopp's theorem in real analysis. Okay. Oh, no. Oops. Okay, so now we're going to look at a special case. So I'm not going to look at the general vibration. I'm going to look at the very special vibration, which is actually trivial then. So it's just a product. It looks like this. So I'm just going to take one fixed x. So this is just x. All the fibers are, so xy is equal to x. So this is just equal to x multiplied by y. If this thing here is y. So a trivial vibration. But I still have a line bundle, and I still have a semi-positively curved metric there. Okay, then we can take, we also take the line bundle to be, so all the fibers are the same, and I also take the line bundle to be the same. So the line bundle here, L, no. Yeah, so the line bundle here is just the pull. Yeah, sorry, I'm specializing even more now. So I'm taking the line bundle to be the same, and I also choose L to be equal to negative of the canonical bundle of X. So the dual of the canonical bundle. Are you raising your hand? No, you're not. Okay, so I still have the canonical bundle there, and then I choose my L to be the negative of the canonical bundle. So then the twisted bundle here, the bundle of n forms with values in the anti-canonical bundle, is just a trivial bundle. So I just have here, I'm not looking now at any fancy space of holomorphic n forms with values in a line bundle. Well, actually I am, but it reduces to just looking at holomorphic functions on the space here. And since they are actually holomorphic functions must be constants, so I'm just looking at constants. I'm looking at L2 norms of constants, which is sort of a volume of the manifold, if you want to. So then it corresponds even closer to what I had before there. Now, this bundle here, the bundle that I get in this case, has a trivial section, which I call U, but U is actually only one. It's a basis for the space of constant function. There's one all over here. It's a holomorphic section of this bundle E. So E I get in this case. E, the way I defined it before, is just now equal to, it's a line bundle. It's a trivial line bundle. And the fact that this trivial line bundle has a positive curvature means precisely I can think of my metric. I have a metric on L that is a metric on the anticanonical bundle, and that corresponds to a volume form. So this is actually the pointwise norm of the trivial section u equal to 1. It becomes a volume form here. And then the theorem just says the following. It says that if I take this volume form and I integrate it over all the fibers here, and I let the fibers move, then I have that this is, but with a minus sign, is plurisubharmonic. So that corresponds to saying that the logarithm of those integrals here have some concavity property, just like in the situation over there. That's something I should, is it more or less understandable? Yes. To you, yes. Okay, so then we can take any base here for this, but actually now I will specialize even more. So I will say that Y here is a strip. So it's just a strip in C. The complex manifold is just a strip, the set of complex numbers such that the real part lies between -1 and 1. And we also assume now that my metric here, which will then depend on the base variable here, that it depends only on the real part of the base variable. So then I get a function here that depends only on the real part, and this is plurisubharmonic. It just means that this is a convex function of t. So the logarithm of this integral here is a convex function of t. So this I call the complex Prekopa theorem, because it is a complex version of a theorem of Prekopa, which says that this thing here in the real setting, before I integrated over the fibers of a convex body, now I integrate over all of Rn. It's not a big difference. They're sort of equivalent to each other in a very easy way. And Prekopa, as I said before, is a generalization of the Brunn-Minkowski theorem. You can think of this complex statement as a generalization of the Brunn-Minkowski theorem in this way. So the difference is that in this particular setting that I had here, I'm only integrating, I have constants here. In the general setting of the theorem, I had some norm of a holomorphic section, but now the only holomorphic section is 1, so I don't write it out. So I skip to, and you can, we can prove this. One proves this in much the same way as one proves this special case of the theorem. One can prove in much the same way as one proves the Prekopa theorem in real analysis, basically just by differentiating this thing here twice. But then you have to apply something, and this thing that I apply here in the end will be Hermander's L2 estimate for the d-bar equation. That's the thing that makes give me the right sign in the end there. But this is a statement that, well, this is the real statement, and the complex statement looks very similar. It said that such things here are convex, but these are now not convex functions, but they are metrics on the anticanonical bundle. Okay. Now, the thing that is related to uniqueness theorem in Kähler geometry is the following question. That we know that this function here is concave, but when do we, so to speak, have equality in the inequality? When is it not strictly concave, but for instance, linear? When is it a linear function? What can you say then? Well, we look at the real analog. We have Prekopa's theorem. So this is a concave function. No, this is a convex function since I have a minus sign there. Then it is known that if this is linear, then actually those functions are almost independent of t. It's just equal to one fixed function, but you translate it in some direction. You choose a fixed direction v, and you translate the variable x plus tv. So you can express that in a more geometric language to say, by saying that you get one metric from the other one by flowing with a constant vector field. That's the only way that you can vary the thing if you want to have linearity instead of convexity. Okay. Now we ask the same question in the complex setting. And the main difficulty of the theorem here is that I have rather weak conditions on the metric. So I have this phi t. I assume only it's locally bounded and that it satisfies this thing here on the total space. So IDD bar with respect to the fibers and the base variable simultaneously, that means IDD bar on the total space should be greater than or equal to 0. Then I have this technical assumption. Actually, when I prepared the lecture now, I didn't remember why I put that assumption in there. I'm not quite sure that you need it, but well, let's forget about that. That's a not important thing. And then you assume that this is linear. In that case, those are basically, it's the same thing as in the real Prekopa theorem. You get from one volume form or one metric to the other one by flowing, but now with respect to a holomorphic vector field. But to state it more easily, I say it in terms of the induced Kähler forms. You take IDD bar of this, IDD bar, the induced metric, the Kähler form that each such metric defines here. You get from one to the other by flowing. You apply in the time one flow of a holomorphic vector field. That's the main result. So that's a generalization of the equality case in Prekopa's theorem. This is when X is Fano or satisfies something a little bit weaker. Because if I had assumed here that I had strict inequality, then it would imply that X would be Fano, because then I would have a metric on the anti-canonical bundle of positive curvature. Now I only assume that it is semi-positive. So it's a little bit weaker than Fano, but basically it's Fano. And also this technical assumption that I don't remember if I need, it's automatic in the case of Fano. So what? Okay, what does it mean? Yeah, it just means that I can solve all d-bar equations. So if f is 0, 1, and d-bar f equal to 0, should imply that f is d-bar exact. If it's d-bar closed, it should be d-bar exact. That's the condition. But it's automatic in the case of Fano manifolds. There is a variant of that then, but then I would have to go into a lot of special cases. So morally, the thing is that the conclusion should be that if it's not a product, then actually as a conclusion, it is a product. But you can only say that. That's only true assuming that you have strict inequality. Otherwise, there are some counterexamples. If you know. Okay, so why, as I said before here, this is fairly easy to see from the proof in case you assume that this metric here is smooth and strictly positively curved on the fibers. Then you have an explicit formula for the curvature, and you can more or less read this off from that formula. But in case here it's only assumed to be locally bounded, then the proof is harder because I don't have any analytic tools to work with. So that's where the difficulty of the theorem lies. Then the natural question is, why bother? Why do I want it to be locally bounded? And why not be happy with assuming that it's smooth anyway? Well, that's because in some applications, we don't have regularity. We cannot prove regularity, either because it's not true or maybe we can't prove it. So I will explain one such case here, and that involves the Mabuchi space of metrics on a positive line bundle. So let's recall what that is. Yes, let's recall what that is. Yeah. So we have an ample. So now I assume that the line bundle is ample, which means that it has a metric, some metric of strictly positive curvature. And then Mabuchi space is the space of all such e to the minus phi that are smooth metrics, and I assume they are strictly positively curved now. So Mabuchi and Sams and Donaldson and many others, but I think it was first Mabuchi, introduced a Riemannian metric on this space. You can compare it to a Riemannian metric on the space of convex functions. I'm not going to write down the Riemannian metric. I'm just going to say that the upshot of it is that a geodesic for that metric is a curve, a real curve of functions in there, or metrics in there, that satisfy those two conditions. First, it should be plurisubharmonic on the total space. IDD bar on the total space should be positive. And then it should not be too plurisubharmonic. So if you raise this thing to the n+1, so you have the Monchampère operator, then this should be 0. The Monchampère with respect to all the variables should be 0. Then it is a geodesic in the space of metric. So I want to, you see, in particular, such geodesics will satisfy the hypothesis I had in my complex Brekopa theorem, because they satisfy this assumption, which means that it's plurisubharmonic on the total space. Now, there is an important theorem of Chen, Chu-Chong Chen, that implies that if you have any two metrics in such a space, such a Mabuchi space, you can connect them, not quite by a geodesic, but a generalized geodesic. So that's a continuous curve that satisfies both those things, but it's maybe not smooth, and it's maybe not strictly positively curved. It may land outside of Mabuchi space. IDD bar might not be strictly positive. But these are called generalized geodesics in this business. And Chen proved that you have some sort of regularity, namely those second-order derivatives here have coefficients that lie in L infinity. So they're not so bad. They're just a little bit less than C2, a little bit less than C2. But it means that most analysis tools don't really work so well there. But they are certainly bounded. I mean, even the second derivative is bound. And moreover, if you just want to have a bounded geodesic, you can prove it without using the difficult proof of Chen. It's a very easy consequence of the Perron method that you can actually find weaker geodesics that satisfies the hypothesis in my theorem, namely that they are just bounded. So there is some the problem of existence of regular geodesics. It's a delicate business, and in my view, it's not completely understood yet. Okay. Now we have to introduce yet another character in the play here, and that's the Monchampère energy of the metric. So the Monchampère energy is a function on this space of metrics on an ample line bundle, and it's defined by the following formula. I will not tell you what it is, but I will tell you what the derivative along a curve is. So the derivative along a curve of this function is given by this horrible expression. Not so horrible, actually. The formula, you can write down a formula for E also, but that's longer and more complicated, so I don't want to do that. And this V here is just some normalization constant, so that this volume form here divided by V becomes a probability measure. And there is a fundamental fact of life of this Monchampère energy, and that is that it is linear along geodesics and even generalized geodesics. And it's well defined even if this metric here is not of class C2. It's enough that it's locally bounded, which is the situation that I'm dealing with. It's still the Monchampère energy, still well defined, and it's still linear along generalized geodesics. So why do we want all these things? Well, it's because it's related to, first, the Ding functional that comes here. The Ding functional for any line bundle, well, no, actually, it's for L equal to the anti-canonical bundle now. So now I'm in the Fano case. I assume that the anti-canonical bundle is positive, and I define the Ding functional as this Monchampère energy plus exactly this kind of thing that I was discussing before, the logarithm of integral e to the minus phi. Remember that the metric on the anti-canonical bundle can be thought of as volume form, I take the mass of that volume form and I do this. Then I get the Ding functional. The motivation for the Ding functional is that metrics that are critical points of this. So I take the variation with respect to phi here. The critical points, they will satisfy this. Because when I take the derivative of that, I will get integration against that. And when I differentiate that, I will get this. So the critical points of the Ding functional will satisfy this equation. Is that clear? Yeah. Differentiate there and differentiate there. There it's an exercise in chain rule, and there it's the definition of the Montrampere energy. So they will satisfy this, and then I can take the logarithm of the whole thing and take IDD bar, and I will get, this is just a constant, it's just a constant to disappear. I get IDD bar of phi here, and on this side I will get the Ricci curvature. So the critical points of this Ding functional are the Kähler-Einstein metrics. That's the important part. That's the important part. So, and then the conclusion of the Prokop theorem says that the Ding functional is convex along generalized geodesics. But we also know when it's strictly convex or when it is not strictly convex. So we can apply that now to the Bando and Mabuchi uniqueness theorem, which is an important uniqueness theorem in Kähler geometry. So that's, it says the following. Assume that we have two different semi-positively curved metrics on the anti-canonical bundle, and they both solve the Kähler-Einstein equation. Then by Chen, we can connect them with a geodesic, a generalized geodesic. The endpoints are both critical points, so the derivative of the Ding functional along the curve vanish at the endpoint. So we have a convex function or a concave function, which has a derivative 0 in both endpoints. So it must, I said it's linear, it's actually constant. No, if you have that, if the derivative 0 in both points. So it's actually a constant. So then by the main theorem, there is a holomorphic vector field with time one flow such that this, the pullback of one of those metrics becomes the other metric. So it means that you have uniqueness of Kähler-Einstein metrics on a Fano manifold up to the action of the flow of a holomorphic vector field. And that is the Bando and Mabuchi theorem. Yeah. And this proof that I sketched here was first done by Robert Biermann, who didn't use this general formulation with bounded geodesics, but he proved directly that in this situation, the geodesic will actually be smooth. So then you didn't need the full theorem for that. You could just use the simpler version for smooth geodesics. So why are we still, then question remains, why are we interested in the non-regular case then? Well, before I get to that, there's another interesting application of this little theory here, and that's connected with Matsushima's theorem from Kähler geometry. So that's actually based on an observation by Chen, Donaldson, and Sun in their paper giving the solution of the Yao-Tian-Donaldson conjecture. They observed that the vector field that one gets here in my theorem, it has a particular property. It's actually not unrelated to the situation that appeared in Professor Fotaki's talk in this morning. It has this particular property that its imaginary part is a holomorphic vector field, but its imaginary part is Hamiltonian for this scalar form. Yeah. So that the imaginary part is Hamiltonian means that it generates a group of isometries on the manifold for this metric. Now, if you have a Kähler-Einstein metric on a manifold, and you let omega 0 be the metric, the Kähler metric defined by that, omega 0. And now you take any automorphism of your manifold. any holomorphic automorphism. And you just move your Kähler form with that automorphism. You get omega 1 instead. It's again a Kähler-Einstein metric because the equation is invariant. And the main theorem is that my theorem also gives an automorphism F that maps the pullback of omega 1 with this automorphism is equal to omega 0. So I had one arbitrary G, and then I have my F there. If you combine those two now, then you will see that if you compose them with each other, you see that F star G star will preserve omega 0. And what does that mean? Well, that means that this map here, GF, is an isometry for omega 0, holomorphic isometry. But this thing here will lie, because of this property that the imaginary part is Hamiltonian, will lie in the complexification of K. The Lie group K of holomorphic isometries. Because the imaginary part of the vector field here was Hamiltonian, so the whole vector field lies in the complexification of the group of isometries. So both of these things here, this thing here is an isometry, and F lies in the complexification of the group of isometries. So the conclusion is that G also lies in the complexification of the group of isometries. And that means that any automorphism lies in the complexification, and that means that the holomorphic automorphism group is reductive. So that's Matsushima's theorem, that if you have a Kähler metric, then the group of automorphisms is reductive. And this follows then from this theorem. Okay, now finally then, why do we want this non-regular situation? Well, it's because you can apply this now in greater generality. All of this now was just in the standard setting of a Fano manifold, fixed Fano manifold, and Kähler-Einstein metrics, etc., where it's well known. But there are some other situations when it's not so well known. And this, well, let me see how much time I have here. Not sure I will. Well, I can maybe explain that. So I assumed that this thing here had the property that integral e to the minus phi t was phi. Well, no, I assumed that this phi t was locally bounded. But in order for the theorem to make sense, for the statement of the theorem to make sense, you should only need to assume that integral e to the minus phi t is finite. You should be able to allow some singularities, but they should be integrable. I don't know if the theorem holds in that generality. That would be nice if one could prove that, but I know a special case of that. And that is when I let the pi t be like this. So it's a sum of two things. The first thing is bounded, and the second one satisfies only that condition, only e to the minus phi lies in L1, but it's fixed, it doesn't depend on t. So it has some singularities, but the singularities don't move. Then I can prove the same theorem again. Okay, so what does that give us then? Then we can look at this sort of twisted Ding functional. We look at, I say d of chi is this, but I inserted my fixed psi over there. So I fix psi, and then I define a function of the variable chi like this. And then its critical points, we go through the same argument, would satisfy something like that, and they will be then twisted Kähler-Einstein metrics. And this way, we get uniqueness theorems a la Bando and Mabuchi for twisted Kähler-Einstein metrics. So particularly interesting in this case is when this thing here, I dd bar of psi, is the current of integration on a divisor, which may happen. So that's also something that appeared in the proof of Chen-Donaldson-Soon of the Yao-Tian-Donaldson conjecture. They had the formation of metric with conical singularities, and then they had such a divisor term there also. And then the point is that you get uniqueness in the same way. So we get uniqueness theorems of Bando and Mabuchi type for twisted Kähler-Einstein equations, and in particular when this thing here is a KLT divisor, just meaning that e to the minus phi is locally integrable. And this was even further developed afterwards, or approximately at the same time, by Berndtsson, Berndtsson, Essedieu, Gedge, and Serrey. And they generalize it further when the manifold is also allowed to have singularities of a special kind. Singularities of the type that occur in the original proof of the Yao-Tian-Donaldson connection. And then finally, in a parallel way, Chen-Donaldson-Soon used the main theorem and its generalization to prove a version of Matsushima's theorem then on the reductiveness of an automorphism group for twisted Kähler-Einstein metric, for Kähler-Einstein metrics with conical singularities, and on manifolds that may have some singularities. And there's only one slide left, I believe. So let me just say one word before I go to the next slide. There is actually another application as well, and that is, I didn't write it down here because I figured I wouldn't have time for it, and that turns out to be correct. But you can also apply this to Kähler-Ritchie solitons. Exactly. So yeah. Okay, but thanks very much for your time.
Thank you very much for the very nice talk. Okay, any questions or comments?
I can just say what the difference is, because the Ding functional, it looked like the logarithm of the integral e to the minus pi plus Monchampère, like this, right? So in order to study twisted Kähler-Einstein metric, I changed the Ding functional. In order to prove uniqueness of solitons, I changed this, but in precisely the same way as Xu did, so that I most certainly don't pronounce it the right way, but there, the proof of Tian and Xu, it used an energy, a generalization of the Monchampère energy introduced by Xu. So I used that also. I just replaced this by that, and then one gets uniqueness for solitons.
Any other questions?
So the fractional video in the complex report theorem corresponds to the unique case of Brunn-Minkowski.
Exactly, yes. Yeah. Exactly. So it corresponds then to that. And the condition for equality is that there is a flow of some holomorphic vector field. In the Brunn-Minkowski, there is a constant vector field. So it's just a translation in that sense, in that case. Yeah.
So what the video? Flow.
Yes, exactly. I cannot. I can do it. I have a paper on that in the smooth case when the metric e to the minus phi is smooth. Then I have some conditions, of this style for when the thing is when the curvature is when the curvature is 0. But I've not been able to generalize it to the singular case when the metric is has singularities. It's just locally bounded or something. This I don't know in the general case, but only for Prekova. The polarization, but I have a metric also on what do you mean by polar? I have a line bundle. I have a positive line bundle, but and it has a metric that is varying. And this is a question of how regular that metric is. So if it is smooth, etc., then I think for more or less situation, almost always you have the same conclusion. The holomorphic vibration needs to be locally trivial, and the curvature, well, the metric has to move in the same way as here, but under a little bit stronger assumptions.
Any other questions? If not, let's thank the speaker again.